Thank you very much for joining. This is, like I said, it's our first webinar since we released Haystack 2.0. And I'm very pleased today that we have Neo4j as our first guest. And this one is very special because this whole collaboration came about thanks to a community contribution, one of my favorite kinds of contributions. So Sergey, who is the creator of the Neo4j document store for Haystack, is here as well. So the plan is, let's hope this works. Yes, we'll have two talks. First, I'll hand over to Andreas Kolleger, who's developer relations at Neo4j, who'll be talking about knowledge graphs for RAG applications. And then we'll be having a second talk by Sergey, who's going to talk about the Haystack integration for Neo4j as well. Before we get into that, some quick information. So if you are already a Haystack user, maybe you've already heard of this. Just last week, we released Haystack 2.0. This QR code, I'm going to send it in the chat as well, so you'll have the link. This QR code takes you to the announcement article for Haystack 2.0. This was a pretty big deal for us. It's nearly a complete rewrite of our Haystack framework, and it's a lot more flexible to use and build very custom RAG applications, applications that make use of large language models and other kinds of language models as well. And with that, a bit of more news about the coming weeks. So this is the first of a series of webinars and events we're holding. March 28th, we have a meetup in San Francisco, which is supposed to be a 2.0 celebration meetup as well. And we're joined by Cloudflare and DataStax. But if you're not able to make it in person, don't worry, because we also have live streams coming up with both of the speakers we have for that day as well. So the first one will be April 3rd with a live stream with DataStax, and then the second one will be a live stream with Cloudflare on April 12th. And that QR code is going to take you to the Haystack events calendar on Luma. But again, I'm going to post all of the links you need for that when I stop sharing and hand it over to Andreas. So with that, Andreas, the stage is yours. Thank you very much.
Great. Thank you, Twana. Okay, everyone, I'll go ahead and switch screens and get this going. Awesome. Okay, so let's get right into it. This is a great complementary talk. I think the two talks, I'm going to be talking about data, and then we're going to be talking about like how to access that data in the second talk with Sergey. So let's get straight into it. When I think about the data, I always think about like, okay, what are the sources of the data that you've got that you're going to do a RAG application with? And for me, there are really three different data sources to think about, which have different access patterns that come along with them. And so what do I mean by that? When you hear about RAG applications, people will often talk about chatting with your PDF or chatting with some content that's really for me, I call that pure text or pure content as one of the most popular, I guess, ways to start doing any kind of RAG applications. That's either unstructured data that is in PDFs, other plain text files, or maybe even images. So unstructured data or just pure text. This comes along with an access pattern that I think about as being really information search. You've got some idea that there somewhere in this unstructured data is the answer kind of somewhere, right? You just have to find that answer and surface it and provide it to the user. So it's for questions like if you asked about, Apple Computer, like what is Apple's primary business? Hopefully within the documents you've got, somewhere there's a statement that says, well, Apple's primary business is selling iPhones or something like that. And that makes sense for kind of information search. Kind of on the opposite spectrum of all this, if you've got stuff that is unstructured data, there's also structured data, also a good source of doing RAG applications. The typical source for this, of course, is that you've got data in a database somewhere. So that's the classic way to have structured data. Probably came from CSV files or something else, or maybe you actually gathered it from something else, but you've actually put it into a database, so it's got structure now. So there's different access patterns and different information queries you ask about this. So this is more like if you have natural language questions, you try to turn that natural language question into a database query and then run that. And the kinds of things you do with the database query are things like, okay, if you're selling iPhones because your Apple computer, you would ask a question like, how many iPhones did Apple sell in the last quarter? It's a very natural thing to ask of a database. And now you can ask that in natural language through the power of generative AI and LLMs, right? And so you get explicit facts from the database back from the database. You package that up, hand that to the LLM to provide an answer to the user in kind of a chat context. what's interesting is when you think about these two kind of extremes, these boundary conditions, I would say in some ways, you can of course mix them. Sometimes you have some unstructured data and you have structured data, and you can find ways of actually connecting them. And so that ends up being a mix of unstructured and structured data all within one data source. This is when you've got structured data together with like kind of long form text is the typical thing. And if you think about what happens when you create, let's say like a WordPress site, somewhere there's a database that has lots of text, but also lots of structured data around that text as well. And so this is a mix of pure text and pure data. So the access patterns end up being a little bit different. And you also can ask different kinds of questions because you have this mix. And so you could ask things like if you had, information about companies and what their business was, you could ask a question like, okay, for some investors in a company, who are going to be impacted by shortages in chip supply? So if you're relying on NVIDIA chips, let's say, because many people are these days, let's say NVIDIA has, some trouble meeting their current demand, who's going to be impacted that and on the business side, and then what investors are going to be impacted by that. That ends up being a combined search of like in the kind of text, you might find out like who is being affected by chip shortages. And then you could kind of go from like information about a business that needs chips that might be impacted by that as a business risk, all the way back to investors in a company and ask those kinds of questions. It's more like an information discovery type question. Bringing all that together in one data source, you end up with what we call a knowledge graph. A knowledge graph is fundamentally a data structure that uses, graph structure, so nodes and relationships, almost as I've depicted them there. Circles and lines is the classic way to kind of draw a graph. And that lets you bridge from unstructured text all the way to structured data in one data source, and then ask questions about it. The patterns that actually end up emerging, there's a new term that's being used a little bit, where it's not just RAG. If you know you're doing RAG with a knowledge graph, that there's a lot of research and also practical applications of actually doing what's called graph RAG, which is the very particular different kinds of access patterns you have if you have a knowledge graph and how you ask things about information search, discovery, or just information queries. The way you go about doing that generally is if you're just doing pure text, you always start with vector search. And then if you're in a knowledge graph, you start with a vector search, you find some documents, and then maybe you find context around those documents, whether it's a context window or like maybe parent documents and things like that. If you're doing pure data, you're still kind of doing the classic, let's take the natural language, turn that into a query, run the query, see what information you get back. And then in the middle, you combine those two techniques. Do a little bit of vector search, use that kind of as anchoring points for then doing query patterns around the data. So beyond just doing context, also like information that might be related through different structures within the graph. Okay, I'm going to do a kind of work my way up to like what a knowledge graph is now, more particularly through an example using what's called the SEC Edgar financial data. This is an example we've been using a couple different ways with the Neo4j. And if you're not from the US, this is the SEC is the Securities and Exchange Commission. They're the government body that regulates people who are publicly trading information. So investors and also companies that are publicly trading in the stock market. So for companies that are on the stock market, they have to file these Form 10-Ks that describe what their business is about, how they've been doing in the last quarter, what the challenges are for the business, things like that, so that investors know for companies, what is this company that I might want to invest in? Can I find information about that? The company has to let you know. The Form 13s are kind of the flip side of that, or that's for like large institutional investment companies, so management firms really, that have large portfolios of investments. They also have to be public about like what they're investing in and how much they're investing in different public companies. So we created a little knowledge graph that combines these two different data sets, and it lets us do both the structured data and then the structured data together. The kind of strategy that we have for creating a knowledge graph is that we actually start really small as much as we can. We have the idea of a minimal viable graph. You start with the least amount of data that can usefully answer questions, and then you kind of grow a graph around that. And the way you grow the graph is that you look for more information you might be able to add or extract from maybe the data that you have. You enhance that in some way. And then, of course, you create connections. And the connections are what really become powerful over time. The more connections you have, the better the context you can provide for answers that you're trying to look for. And that actually might be useful for users. So looking at the SEC data set, what does that look like? The first step is the classic step. We actually take just the interesting bits of text from these Form 10-Ks. We do a bunch of data engineering first, to be honest. They ended up with some JSON files finally that have just chunks of text. And then we import all that text. And then for each of the text sections that are interesting from a form, we just create some nodes, what are called. So there's the data records inside of a knowledge graph are called nodes. So we create these chunk nodes. And then for each of those chunk nodes, we create text embeddings. And for those text embeddings of the chunk nodes, we then also create relationships between the chunks so that you have some idea like what was the previous chunk and what's the next chunk. So I'm moving along a little quickly. We'll have some time maybe to ask some questions about this if you have any. At the end, this is still the kind of classic pattern I talked through. You're kind of extracting some data here in the creation phase, extracting it from the raw data to create the data records, enhancing it with a vector embedding, and then kind of expanding or connecting the chunks so that they're connected to each other. That kind of pattern repeats a couple of times, and that's how you kind of grow a graph over time. Even with this really tiny graph, all we have is chunks that are connected to each other in kind of a linked list. It's already pretty useful because you already have the idea of like, you can do actually a chunk window. Like, so if you do a vector similarity search, you land on a particular chunk, you can find out how many chunks are before it and after it just by following the linked list. And also because, of course, you've got some metadata available there. Here we have just some very simple metadata, just what's the form that it came from in terms of the ID. So you can actually look that up if you wanted to. But it's a useful, graph already. To elaborate on this a little bit, though, it would be nice to actually have the form around. So you create some nodes for the forms that these chunks came from. And in that form node, you would actually add extra information. You might take a look across all the chunks and anticipate that for some questions, people don't want like kind of pointed, answers. They actually have kind of summary answers that they might want to look for. The form node is a good place to put that kind of information. So you might actually do a little bit of pre-processing and when you're creating the graph here and actually go ahead and like look at a bunch of chunks and ask the LLM, hey, can you give me a summarization of this? And add that summarization itself directly to the form nodes so that then also gets a vector embedding so that for some questions that are, larger questions, you might actually just get that from the summary rather than the individual chunks. This strategy you can apply depending on the different kind of documents you started with. You might have multiple levels from like maybe it's a book with chapters and sections within the chapters. You might find that like, the way you've chunked up things, you might have different levels of chunking and different levels of summarization that you do that tune for different levels and different kinds of questions people ask. Again, for this small graph, it's just two levels. We've got the detail level and the summarization level. Take that one step further. We've got some unstructured data that we've made a small graph around. For the Form 13s, this is the investment management companies. So the people who have portfolios of investments into companies. We take a CSV of actually all that data. We don't care about their descriptions about who they are and what they care about. We just care about their investments. So here we're just going to create some structured data around that. So we create some records for just the managers themselves, some other records for the public companies, and then we have a relationship for every investment. There's a relationship from the manager that owns some stock in that company. And we actually add some indexing here as well. Here, instead of vector indexing, for things like name lookups, it's really more useful to have full text lookup than it is to do a vector similarity search. You don't want to do conceptually similar companies. You want variations on the text you might have mistyped, or like, the way that they've reported maybe is different. So if you're looking for Apple Computer, you might say Apple Computer, but they might have filed as, Apple Inc. That is more textually similar than conceptually similar. And so that's what you want to use a full text search for. Taking that a little step further and continuing to kind of grow a graph around the initial data that you have on the structured side, we know that both of these companies have addresses that they're located at. So we can actually extract that and use the addresses as nodes within the graph as well. What's really nice about this is that you can actually do some pattern matching to look for companies and management investment firms that are at the same location just by seeing who's connected to the same nodes. You can do that, but then you can also add yet another index, a geospatial index, and you can do nearness lookups. So now rather than saying, okay, we know that there's these two companies that are in the same city, we could say for a given city, what are the companies or the investment firms that are near that location or near that city, and do a geospatial lookup based on radius or maybe a bounding box. You can then plug in the connected data to the connected sort of the structured data to the unstructured data by just creating one more relationship. We know that these companies have filed these forms. So we create another relationship from the companies to the forms. And now we have a complete, very tidy, but very useful knowledge graph of structured data and unstructured data all together that can answer all kinds of interesting questions. This is a summary of the process that we went through in creating this graph. We went from just the plain forms, the form 10Ks, pulled out some companies, then added the companies and the management firms, pulled out the addresses, and along the way connected them in interesting ways. This process can continue over and over again. You can apply all kinds of interesting machine learning to enhance the graph, to actually find out different aspects of the graph. You can do things like named entity recognition to find within some of the Form 10Ks, let's say they mention other companies that they do business with. You may be able to actually find those, pull them out, and then connect from the form and from the company. You could have implied business or explicit business relationships that they have with other companies. And then you can find all kinds of interesting patterns around that. So the people, places, and things you can extract from the text, grow the graph based on that as well. Every time you do that, it opens up new questions that can be answered. And the questions become really nicely mapped from natural language to the shape of the graph. So it's really interesting in like the different access patterns that you have. And of course, along the way, to make it most relevant for users, you can use the graph for actually storing user memory as well for each chat session that they have. Just keep track of what they've actually asked, what parts of the graph that they've asked about. So the next time you have a session with them, you can take that context and actually take it into account to help do some ranking whenever you get results. Having, user-based ranking is probably the most useful thing for actually keeping relevance for a particular user, because for them, they want to have an experience that is oriented around them, not oriented around generically the rest of the world, what they care about. It's like, okay, for me, the last time I was talking to you, we were talking about Apple Computer. So if I carry on a conversation, you can assume that I'm probably still interested in Apple Computer. At least that's not a bad assumption to make, for the next conversation. Okay, that was a very quick run through. I hope that I've kept it just under time, and I'm happy to take any questions.
Thank you very much. And yeah, I think that was a really fast but good run through. I now definitely know much more about
A
knowledge graphs than
whirlwind
I.
tour.
Yeah, we do have some questions, and I'm going to read them out loud for the recording.
Okay.
So we have 3 questions. I'm going to start with the first one that actually we get in the Haystack Discord a lot as well. So I'm interested in seeing what your answer is. What do you think is the better strategy for dividing a long text into chunks to improve vector search, supposing that we only have plain text without any structure?
Wow. Okay, so the correct answer is the classic answer, which is it depends. It all is a question of like, what does the actual data look like? You see chunking strategies that run the gamut from like just sentence based to paragraph based to like larger sections, and each of those different strategies you change based on like what are people actually trying to ask about, and also what does the text provide. If it's a lot of, you know, creative text, let's say, not just, a bunch of statements of facts, then bigger chunks are helpful because there's not usually a direct answer to a user's question. So you want bigger chunks at that point. But if your source material is more, let's say, even academic, where it's very terse and like focused, like, it is every word matters and is valuable, then you probably actually want smaller chunks because you actually want something that is very particular to what somebody's asking. At any time, though, either strategy you pick, probably you want something that is going to be matched well with the questions, but also then expands a little bit to provide a window. Because my favorite example here is the bomb diffusing example, which doesn't come up very often in RAG applications, I know. But if you're trying to defuse a bomb and you hit the perfect chunk that has the instructions for defusing the bomb, that's really awesome. Unless the very next chunk says, but first, don't touch the red wire. Okay, that's very important to know as part of the answer, right? And so sometimes context really matters, and in all of that, it's contextual. It always depends. How detailed you want, how much context matters, and the only way to get to the right answer for it depends is to do evaluation. That is true in every step of, doing work with Gen AIs, from training all the way to RAG. Here's some sample questions, run them through your pipeline. Are you getting the kind of answers you want? Then good. If not, then bad. And continuously do that evaluation. As users are asking new questions, add that to your backlog, make sure that you're getting good quality. Human kind of evaluation and then automated evaluation as a follow-on is critical for good RAG.
Yeah, and unfortunately, it depends is usually our answer as well. It's not, yeah, it's usually not what people want to hear, but it is unfortunately the case. There is another question. Do you have any data about what the average time used to ask queries in a database with thousands and millions of nodes is? So I'm guessing how long it takes to retrieve an answer.
Right. So that also depends on what strategy you've used for doing the queries. So the general rule of thumb for query time in Neo4j is that query time is linear proportionate to the number of relationships involved in finding an answer. So what does that mean? So that ends up meaning like if you're just doing kind of a vector search approach and all you're doing is I know that the answer is going to be in a single chunk. Okay, that's just basically a vector search, find the chunk, return it. Super quick. Even if you're finding, a window of chunks around that, finding those 2 chunks around or 3 chunks around, that's just following pointers, basically. Like it is literally like getting a linked list and just getting the neighbors and passing that back. So that is incredibly fast. If you're doing something more on the information query side of the house, so like you're doing some kind of here's a natural language question, and I actually have to generate some query to run, and let's say that all happens correctly, it is possible to ask questions that require where the answer isn't just a local part of the graph, but it's more an analytical question. Like, okay, I have to look through the entire data set and summarize an answer. Those questions then take longer because you're touching more of the graph. So that is still, the answer still depends whether it's a very localized focus, let me get this information, or am I looking at the entire graph and trying to summarize things, and then it's everything in between.
All right, thank you. I think I'll ask you one more question. There's a lot more coming in. So what we'll do is I'll ask one more question live, and then while Sergey is presenting his talk, maybe we can answer some others in Q&A in written form as well. All right, so I'm going to pick at random. And yeah, let's go with this one. How would you recommend combining structured and unstructured search for RAG, like retrieving a node that focuses on just a location, then maybe processing the description property or nodes it's related to?
Yeah, so actually what was described here, I think is a sensible place to start, like that the initial exploration of kind of doing information discovery type questions, it's usually anchored in something you know. So whether that's through vector search or geospatial or something else, find a place to start at the graph, and then you expand either through the unstructured data to find more an expanded context window, or you do a context pattern that goes into the structured data as well. And again, it depends. There's some, art to this about trying to map what is the right context for a user's question. There are a couple different strategies there that I think are more time than we want to get into right now, but I'd be happy to do a session on that. But the general idea is like find a place to start and then find a pattern around that, a local context.
All right, thank you very much.